In this talk, I'll be presenting our paper titled Neighbors from Hell: Voltage Attacks Against Deep Learning Accelerators on Multi-Tenant FPGAs. This is a joint collaboration with Matthew Ho, Nicolas Papanou, and Von Betz from the University of Toronto and the Vector Institute for Artificial Intelligence. First, let me start by describing the motivation behind this work. We have recently seen FPGAs being deployed on a large scale in data centers. For example, users can rent out F1 instances from Amazon AWS, which have up to 8 FPGA cards. We have also seen the very successful Catapult and Brainwave projects from Microsoft, in which each server is coupled with a network-connected FPGA, which together can form a data center scale deep learning inference accelerator. And similar cloud FPGA services are also offered by Baidu. With the adoption of FPGAs in data center, researchers are expecting that FPGAs will soon be viewed as virtualized data center resources, with the physical device details abstracted away from the users. In such scenario, incoming tasks are mapped to a pool of available hardware resources. This virtualization model would also allow the sharing of the same physical device among different users, as the case with data center CPU servers. However, virtualizing FPGA resources is more challenging than conventional data center CPU servers. Typically, the service provider designs a shell, which provides common infrastructure such as external memory, PCIe, and network interfaces for multiple user roles. These user roles are partially reconfigurable regions that implement the user-specified application logic and can be swapped in and out without disrupting the operation of the rest of the FPGA device. This model allows user-friendly FPGA deployment since the user doesn't have to care about designing or meeting the timing requirements of the device-specific system infrastructure, but rather focus on designing and optimizing only the application logic. But what if one of the users is an adversary? We really have to be aware of how much damage can be done by a malicious FPGA tenant and how to prevent it in order to unlock the potential benefits of this FPGA virtualization model. Now let's take a quick look at different multi-tenant FPGA attacks that have been shown in prior work in this area. The first type of attacks is extraction attacks. In these attacks, the adversary is trying to gain unauthorized access or steal the victim's data. This was shown to be possible by exploiting the crosstalk between long wires in the FPGA routing fabric, or by performing differential power or fault analysis to infer some characteristics about the victim's data, or even obtain a copy of it. The second type is denial of service attacks, in which the adversary's main target is to crash the whole FPGA device. This is typically achieved by drawing a large amount of current by forming short connections on the FPGA, or by implementing what is known as power hammering circuits that have very high switching activities and current consumption, such as ring oscillators, for example. Finally, the third type of attacks is integrity attacks, which aim to break the functionality of the victim circuit by causing voltage drops in the shared power distribution network of the FPGA, which injects timing faults in a neighboring row. This has also been achieved by using asynchronous ring oscillators. As we have seen, most of the attackers rely on some form of fast-toggling combinational loops such as ring oscillators. But such malicious circuits can be detected by netlist and bitstream verifiers. In fact, this is a well-known defense technique that is already deployed in Amazon AWS. Our work in this paper is an example of integrity attacks. In this work, we try to answer two main questions. Is it possible to inject faults in a victim circuit using adversary circuits that wouldn't be detected by conventional bitstream verifiers, and whether these adversary circuits can compromise the accuracy of the deep learning accelerator implemented in the victim role or not? In the rest of this presentation, I'll first describe the attacker circuits that we experiment with. Then I'm going to present some results to evaluate the attack feasibility and strength. And finally, show the outcome of using these adversary circuits to attack a deep learning accelerator in a multi-tenant FPGA scenario. Okay, so let's start by describing the attacker circuits. We experiment with three different attacker circuits. The first one implements a conventional two-dimensional array of asynchronous ring oscillators similar to what is used in most of the prior works. Each of these ring oscillators is implemented using an AND gate, with its output feeding back into one of its inputs, and has two control signals: an enable signal that turns the ring oscillator on or off, and a toggle signal that is toggling at a user-specified frequency to periodically start and stop the oscillator. Each oscillator can be implemented in a single FPGA lookup table, and its oscillating frequency depends on the routing delay between the NAND output and input, which can be in the order of several gigahertz in modern FPGAs. This attacker circuit serves as the baseline that we compare the other attacker circuits to. The second attacker is what we call the clock-gated garbled XORs. This one consists of a set of toggle flip-flops that feed different 4-input XOR gates. The output of the XOR gates change when any of its input change, creating high switching activity. All the flip-flops in this attacker are clock-gated using vendor-supplied clock-gating IPs. And really, the whole idea behind this attacker is that clock gating a large portion of an FPGA design could cause sharp transients or significant current change over a short period of time, especially when the gated circuitry is enabled or disabled. This would potentially cause voltage drops, leading to the injection of timing faults using a normal circuit that bitstream verifiers won't catch. The last attacker uses the same clock-gated garbled XORs implemented in the FPGA's soft logic, but also uses, in addition to that, the hard blocks, such as DRAMs and DSPs, to create an even higher switching activity. At each clock cycle, a checkerboard pattern is written in red from sequential addresses in each of the DRAM blocks in the attacker circuits. In addition, all the DSP blocks are seeded with random initial inputs, and the produced output is then fed back again to the DSP inputs. The DRAMs and DSPs are also both clock-gated, similar to the garbled XORs in the soft logic. In summary, one attacker that uses the asynchronous ROs is detectable by bitstream and netlist verifiers, while the two other clock-gated attackers using soft logic only or a mix of soft and hard logic cannot be detected, as they do not include any combinational loops and use vendor-supplied IP cores for clock gating. We perform our experiments on an Intel Stratix 10 GX2800 card, which is the largest monolithic Stratix 10 FPGA. We floor plan the device into two physically isolated rows that are roughly equal in size, and all three attacker circuits that we implement fill more than 75% of the adversary row. And the clock-gated hybrid attacker uses more than 87% of the available hard blocks in the adversary row as well. Now, since you know the attacker circuits that we use in our experiments and their implementation on the FPGA device, I will continue with describing how we characterize the integrity attack using these different attacker circuits. This diagram shows the victim circuit that we use in our attack characterization experiments. We use the circuit to detect when a specific path fails timing at a specific operating frequency. It starts with a launch register that toggles its value every cycle, then propagates the signal through a delay chain that is CL stages long. It is then sampled after half a clock cycle, and then the sampled value and the output of the delay chain are compared using an XOR gate. If everything is working as expected, the mismatch register is going to hold a value of 0, which indicates that no timing failure was detected. But if the attacker managed to successfully create voltage drops, it will take longer time for the signal to propagate through the delay chain. Therefore, the sampling register will capture a wrong value, and the mismatch register will be set to 1, indicating a timing failure. Our experimental testbed is implemented on a Stratix 10 GX device, as we previously mentioned, and we use Quartus Prime Pro 19.3 to implement our design and generate the bit streams we use in our experiments. Our testbed consists of 5 different arrays of 320 victim circuits each. Each array has a different delay chain length ranging from 5 to 9 inverter stages. These victim arrays are all clogged using a reconfigurable PLL to allow us to sweep their operating frequency, and in addition to that, there is the attacker circuitry, which implements one of the 3 attacker circuits we previously explained. All these modules are wrapped as Avalon memory mapped IPs that communicate with a host CPU over PCIe and an Avalon memory map bus. The host CPU can read out the mismatch registers of all victim circuits and also enable or disable different parts of the attacker circuitry. The mismatch register values of the victim circuits are then post-processed on the CPU to generate the results that we're going to present next. We also study the effect of floor planning on the feasibility and strengths of the attack by having 2 different variations for each experiment. The first one is a non-floor plan variation in which the CAD tools decide the placement of both victim and attacker circuits. The second variation assigns a separate logic logged region for each of the victim and the attacker circuits to mimic physically isolated roles in a multi-tenant FPGA scenario. These graphs show the attack characterization results for the more realistic floor plan case of the three attackers using asynchronous ROs on the left, clock-gated garbled XORs in the middle, and clock-gated hybrid logic on the right. The line graphs show the number of paths that are expecting to fail at different operating clock periods based on the timing report from Quartus. The bars represent the number of paths that are actually failing in hardware at the different operating clock periods that we perform our measurements at. The three rows show the results for victim circuit arrays of different chain length, and the frequency that we run the victim circuits at increases as we move from the right to the left of each graph. When all the attacker circuits are off, we can see that, as expected, no paths fail timing when Quartus expects them not to fail timing. This is indicated by the values of the bars being less than or equal to the line graphs. The graphs also show that as we increase the operating frequency of the victim circuits, more and more paths start to fail timing. When we turn on 50% of the ring oscillators in the first attacker and enable the toggling logic in the other two attackers but without periodic clock gating, we can see that significantly more paths start to fail timing. At every point where the bar value is higher than the line curve, a path that Quartus thought it was safe to run at a specific frequency is actually failing timing. The problem becomes even more severe when we increase the percentage of enabled oscillators to 87.5%. Or start periodic clock gating in the other two attackers as indicated by the incremental increase in the bar heights. If we enable more ring oscillators beyond 87.5%, the whole FPGA board crashes and we are able to reprogram and use the FPGA again only after power cycling the whole server. These results also show that the attackers that do not look malicious, or in other words, do not contain combinational loops, can be as effective as ring oscillators. In order to investigate the effect of floor planning the attacker and the victim circuits into separate physically isolated roles, we generate these heat maps for the number of detected timing violations. Green shades indicate the number of violations detected when running the victim circuit at a frequency higher than the safe operating frequency reported by Quartus, while the red shades indicate the timing violations detected when running the victim circuit at a frequency lower than the safe operating frequency. In other words, a green violation means that it is expected according to the Quartus timing report, while a red violation indicates a successful integrity attack since Quartus reported that the circuit should run safely without any problems at these frequencies. We show this for different chain length and different percentages of enabled ring oscillators on the x-axis, with the upper set of heat maps showing the results for the non-floor plan case and the lower one showing the results for the floor plan case. The maximum safe operating frequency reported by Quartus is indicated by the black horizontal lines. The first green shade, when no ring oscillators are enabled, indicates the lowest operating frequency at which any path starts to fail timing in our hardware measurements at normal operating conditions without any attacker circuits enabled. And therefore, the difference between the first failing path, or the first green shades, and the black lines indicate the timing safety margins introduced by the Quartus timing analyzer. From these heat maps, we can deduce the following. First, the integrity attack was successful in almost all of our experiments as indicated by the red points in the heat maps. The attacker circuit can successfully inject timing faults and break the victim functionality at frequencies that Quartus thought were perfectly safe to run at. Also, floor planning tenants into physically isolated roles does help, as the number of red points are less in the lower graphs compared to the upper graph. But it definitely does not prevent the attacker from injecting timing faults into the victim circuit. And finally, we can see that Quartus introduces a safety margin of 5 to 21% of the reported minimum clock period, and this was consistent across multiple compilations and seeds. All our experiments were conducted on a new StratXtend card, but over time, we would expect these margins to be reduced by transistor aging effects, which further increases the severity of such integrity attacks. Now let's look at the attackers that won't be detected by bitstream verifiers. And let's also assume that roles are floor planned and isolated for better security. The upper set of heat maps are for the clock-gated garbled XORs, and the lower set is for the clock-gated hybrid logic. The heat map showed that the integrity attack is also feasible when using the innocuous circuits that wouldn't be detected by bitstream verifiers. In fact, the clock-gated garbled XORs are as effective as ring oscillators in injecting timing faults into the victim circuits. The use of hard blocks like DRAMs and DSPs in the attacker circuit can enhance the attack strength as the number of red points in the lower heat maps increases compared to the upper ones. This means that even a benevolent circuit that has high switching activity and uses aggressive clock gating as a power-saving mechanism for a large portion of the FPGA logic can unintentionally inject faults in neighboring physically isolated circuits. The third and last part of the presentation describes a case study that we perform in which we use the clock-gated adversary circuits to attack a deep learning accelerator in a physically isolated row. The fact that deep learning models are resilient against computational errors is already well established, and is even exploited to achieve higher performance. One example for that is model compression, in which most of the model weights can be pruned out without affecting its prediction accuracy. Also, another example is weight quantization, which enables the use of the much cheaper fixed-point numerical representations down to even ternary and binary precisions with negligible or even no accuracy loss. But what about timing faults in the underlying hardware? Are deep learning models also resilient against those? If so, we can consider the accelerator frequency as another knob that provides a trade-off between performance and model accuracy. In this case study, we use HPipe, an FPGA-optimized state-of-the-art CNN accelerator, which in fact you'll learn about in another session in this conference. This accelerator runs a dense image classification MobileNet V1 model using 16-bit fixed-point precision. We generate an HPipe instance that is small enough to fit in one of the two physically isolated roles to mimic a multi-tenant FPGA scenario, and its maximum operating frequency is reported by Quartus as 540 MHz. We sweep the operating frequency of the accelerator from 500 to 750 MHz, once with the attacker role disabled and another with the attacker role enabled with periodic clock gating. In almost all CNNs, the output of the final fully connected layer goes through a softmax layer that generates the final predictions of the model as shown in this figure. So for each experiment that we run, we measure two things. First, we record the model's classification accuracy over 50,000 test images, and second, we measure the difference in angle between the CNN output before the final softmax layer and its golden reference output that we pre-recorded at normal operating conditions, running at a safe frequency without any attackers enabled. This metric is intended to capture the numerical differences in the CNN output that is calculated by the deep learning accelerator, which might be caused by injecting hardware timing faults. These curves show the top one classification accuracies, which basically means that the model gets the right answer at different operating frequencies with the attackers completely disabled. These other curves show the top 5 classification accuracy, which means that the right answer is one of the model's top 5 guesses. And the bars represent the angle difference between the CNN output and the golden reference output in degrees. You can see that as we increase the operating frequency, more paths start to fail timing in the accelerator, causing the prediction accuracy to gradually drop and the angle differences to increase. The results show that we can overclock the accelerator by 28% to 31% without affecting the prediction accuracies, which is higher than the timing safety margin introduced by Quartus that we quantified earlier to be between 5 and 21%. This is a side effect of the resilience of deep learning models to computational errors, which is indicated by the non-zero angle differences in the graphs. The red curves and bars show the same results, but when enabling the attacker role during conducting our experiments. The enabled attacker circuits reduce the safe overclocking margin to 18.5%, and the deep learning model still shows resilience to the induced timing faults, as there is a noticeable difference between the numerical values of the CNN output calculated by the accelerator and the pre-recorded reference outputs, which still does not affect its overall prediction accuracy. To conclude, if we go back to the two questions that we were trying to answer in this work, the bad news is that, yes, we can inject faults using adversary circuits that cannot be detected by conventional bitstream or netless verifiers. And in fact, those can be as effective as the detectable ring oscillators in injecting timing faults. We show that aggressive clock gating, which is a common power-saving technique, can cause voltage drops and induce timing faults in neighboring circuits. And the good news is deep learning models have an additional hidden safety margin against timing faults. And this is due to their resilience against errors in their computations. Based on our experiments, we could not compromise the prediction accuracy of the deep learning accelerator when running at a safe operating frequency, even when using our strongest attacker circuit. But we can exploit this higher resilience of deep learning models to gain 18% to 31% higher performance by safe overclocking. This can be achieved by having multiple timing violation detection circuits sprinkled around the deep learning accelerator to detect potential voltage drops in the shared power distribution network, and dynamically scale up and down the accelerator's frequency based on its operating conditions. This concludes my presentation. Thanks a lot for your attention, and I will be happy to answer any questions in the discussion forums or over email.